talk about the concavity of a curve. The second derivative measures the rate of change of the first derivative, but the first derivative measures the slope when we're looking at the picture. So in other words, the second derivative is measuring the change in the slope, and that's what we call concavity. If that second derivative is positive, then the curve must be concave up, because what are we saying? We're saying the change in the slope is positive, so it's getting bigger. The slope's getting more positive. So if we look over here at our parabola, we start with a negative slope, but as we're moving along, it becomes positive. So it's increasing in value, if you like. Other situation we would have then is if it's less than 0, the curve would be concave down. Now, if it's equal to 0, it's a possible point of inflection. Doesn't mean it is a point of inflection, but it means it's worth investigating further to see if it is a point of inflection. So this time we're going to draw a very rough sketch, and it will be a very rough sketch. All we're going to use is the second derivative to come up with this picture. So let's find our derivatives then. There's our first derivative, there's our second derivative. So I'm only going to use the second derivative. What does the second derivative tell me about? It tells me about concavity, and all I'm interested in is when is it positive, when is it negative. So let's solve when is it positive. I know when x is greater than -5 on 3, the second derivative is positive. So at -5 on 3, that's when it becomes concave up. Logically then on the left hand side it must have been concave down. As I say, a very, very rough sketch, but it must have that sort of shape. And I know it's going to change concavity at x equals -5 on 3. That now allows us to find these turning points a bit more efficiently. Because if I combine with what we talked about with stationary points with the idea of concavity, then I can classify them very quickly. Because all of our turning points we know are stationary points. They've got a horizontal tangent. Therefore, if I also know it's concave up, it's got to be a minimum turning point. And if it's concave down, it's got to be a maximum turning point. So pulling it all together, if I now had to find these turning points and classify them, first thing I do is find the tools I'm going to use, and that is the derivatives. There's my first derivative, there's my second derivative. Let's locate those stationary points. All right, stationary points occur when to y dx equals 0. I'm going to solve this quadratic. I come up with two answers, a third and -1. So now rather than drawing the table of values, I can just substitute straight into the second derivative. The actual number itself's not that important. What I'm interested in is it less than 0 or greater than 0, because that will tell me concave up or concave down. -4 is less than 0, so I know I must have a maximum turning point because it's concave down, got to be at the top there. And then when I sub the other one in, I get +4, and that's a concave up curve. So therefore that's a minimum turning point. Now that doesn't mean we throw away the idea of testing values, because I might have a function where finding the derivative is difficult, and it might be quicker to test either side of the first derivative than going and try and find the second derivative. So we still use both tools, it just is which is more efficient. Well, let's talk about that other possibility, the possible inflection points. What is a point of inflection? When you reflect, the image stays the same. That's reflection. Inflection is when it changes concavity. So if you think about it, if I was going to get a concave up and reflect it, it's still concave up. But when it inflects, the concavity changes. So just like we did when we looked at stationary points to classify them, we looked at either side. I can do the same thing here. Let's find the inflection points of our curve, 4x cubed plus 6x squared plus 2. Right, so our derivatives, there they are. I got to find the possibilities. When you write this statement down, it's possible points of inflection. It's not points of inflection, they're possibilities. Solve it, I've ended up with one possibility. Now, a little bit of logic tells me that this must be an inflection point anyway. It's a cubic. All cubics have an inflection point. Because I've only come up with one possibility, then it must be the inflection point. It's probably not good enough for a proof. Let's test either side. So -1/2, I've got to pick a point on the left hand side, I've got to pick a point on the right hand side. On the left hand side I'll substitute in -1, I end up with something that's concave down. On the right hand side I get 12. When I substitute in 0, it's concave up, and so yes, oh yeah, the concavity has changed. That statement is crucial. You're highlighting, yes, there is a change in concavity. So from that I can draw the conclusion that's the point of inflection. So it's not like the stationary points, because when the first derivative is equal to 0, it must be a stationary point. So I can conclude that straight away. But with the second derivative one, it's a possible inflection point. So I have to justify why that works. Oh, I know there's a change in concavity, therefore it is an inflection point. Then we have these very special points of inflection, the horizontal ones. They're the ones where the first derivative is equal to 0. Hence the name horizontal point of inflection. The tangent is horizontal. The second derivative will also equal 0, but the third derivative will not equal 0. Hang on. That brings me to this idea, an alternative way of finding inflection points. We know this. We know possible points of inflection occur when the second derivative is equal to 0. If the first non-zero derivative is of odd order, so in other words, you keep differentiating. If the first time when you substitute in, you get an answer that's not 0, and it happens to be an odd derivative, it's a point of inflection. So the one I just said before was the third derivative. But it might not be the third, it might be the fifth, it might be the seventh, it might be the ninth. It depends how far you have to keep going. If it's an even one, so fourth derivative, sixth derivative and so on, then it's not a point of inflection. Now why? Because what does the derivative measure? It measures a change. So the third derivative measures the change in the second derivative, or the change in concavity. And that's what an inflection point is, a change in concavity. So if I come up with an answer which is not equal to 0, there must be a change. If it's equal to 0, we're saying there's no change. So it's not a point of inflection. So with that example I did before, when I'm finding my tools, all I've got to do is just find one more. I'll just find the third derivative. It turns out to be a constant 24. And then when I'm doing my working out, I've found my possible one. All I've got to then do is say, well, x equals -1/2, the third derivative is 24. That doesn't equal 0. So there is a change in concavity. There's how I'm drawing my conclusion. And so yes, it is a point of inflection. I don't have to worry about the table of values. Of course, there's another way you could find points of inflection as well, and that's just using the first derivative. If you were to test either side of the first derivative, because think about what's happening. If, say, it was our cubic here, y equals x cubed, you'd go, oh, look, it's increasing, then it's stationary, then it's increasing. Well, what happened? It must have been a point of inflection. So you could use the first. It's very unusual to use it, but you could. There are other ways of doing things. Okay, so 4E. Oh, exercise, jolly good fellow. There we go.